And then the final experiment, which is quite nice, came later. I didn't do that. I did not have a high-resolution microscope, but my friends in France did. And this is a lattice image of probably the first lattice image of the icosaedral phase. And they performed a diffraction pattern, such as I did, which is nice and dandy. But they also performed another experiment. They took this slide, put it on a transparency, but very, very small. Remember slides? Those days we showed slides. And shone a laser beam through the slide, like that. Very simple, okay? And formed an optical diffraction pattern. And that optical diffraction pattern should look exactly like the electron diffraction pattern, because they both are Fourier transforms from the same image. Here it's the image in the electron microscope, and here is the optical image using a laser beam. And they should look the same. So you can say, okay, big deal. Of course they look the same. Aha. But what you can do, and what they did, was to build an aperture and close that aperture closely to see whether this image disappears or changes into a single crystal diffraction pattern. It did not. Anywhere you shrink it to 0, and this image remained, it becomes fainter and fainter, and finally disappears for lack of information. But it does not change. So, no twins, okay? Which I knew from day one. Why am I saying that? You'll see later. I knew from day one, no twins. I didn't know what it was, but I knew twins were not. This is a modern, more modern image of the icosaedral phase. You can see the tenfold motifs here and so on. And then I went back to the Technion and met Professor Ilan Blech, who helped resolve some issues of the structure, and together we published a paper. Not so fast. We sent a paper for publication to Journal of Applied Physics, and like a ping pong ball from a wall, it bounced back. Whoop, whoop, came back to my desk with a letter saying that this paper will not interest the community of physicists, and we suggest that you send it to a journal of material scientists. And so I did, sent it to a journal named Metallurgical Transactions, and it was published. But it was published more than half a year later. It was a slow publication. Meantime, I went back to, in the summer of 1984, I went back to NBS and showed my result to John Kahn, who was my host. He joined force, brought Denis Gratias, who is a French mathematical crystallographer, and the four of us published a second paper, which was eventually published first. And this was the paper. We should not go into details. But when that paper was published, hell broke loose. A community of avant-garde young scientists joined force immediately, mainly from France, because Denis Gratias went to France and shook the system there. And also in Germany, the United States, China, Japan, many other countries. And immediately a group of young, very active scientists, most of them physicists, but also chemists and material scientists, joined force and started to study these materials. And the number of publications grew in such a way that it was frightening, and I will show you soon why. So, this is the icosahedron, which has the icosahedral symmetry. It's easier for people, especially who like football or soccer ball, to see these symmetries. Like the football has an icosahedral symmetry. And so you can see here, this has a 5-fold rotational symmetry from here. This is a 2-fold, this is 3-fold, and these are the symmetries of the icosahedron. Now, immediately when I started to talk in 1982 at NBS, talk about my results, the reactions were something between mild encouragement, like, Danny, this material is telling us something, and I challenge you to tell us what it is. Find out what it is. This was encouraging. On the other hand, my group leader came to my office one day. He was an X-ray crystallographer. Put a book on my desk saying, Danny, please read this book so that you'll know that what you're talking about is nonsense and cannot be. And I told him, my alloy is not in the book. It's something different. It's not in the book. He was mad at me, came back and said, Danny, I want you to leave my group. You are a disgrace to my group. I don't want my name to be associated with yours. Please go. And so I went. That did not mean any physical movement from my office or laboratory, but it meant reporting to, instead of to his secretary, reporting to another secretary of another group who adopted me, the scientific orphan, and everything was okay, but this was the other side of the reaction. And so from 1982 to 1984, this was the type of reaction that I received from the community. And that was the bad time. If you want to see how I felt during that time, it was something like that. Okay, so when we published the first paper and the community started to grow of believers, then came another opposition. And that opposition was the major serious opposition from the International Union of Crystallographers, and that continued from 1984 to 1987. However, I was not alone anymore. We were a community, a growing community of ambitious, young, active physicists, chemists, material scientists, and architects, and artists, and mathematicians. But the International Union of Crystallography said, you bring us X-ray diffraction or we don't accept what you are saying. Why so? I explained to you before, because this was the Union of X-ray crystallographers. Why didn't I bring them X-ray diffraction results? Because if you want to take an X-ray diffraction from a specimen, the specimen has to have a certain size, not 1 micron, something that you can feel between your fingers, like a grass, like a particle of sand, something that you can put on an edge of a pin and shine an X-ray beam through. We didn't have that. And it took the community 3 years to grow large enough crystals for X-ray diffraction. But my friends in France and in Japan sent me such pictures of X-ray diffraction, lower diffraction, in 1987, and I presented these results in the annual meeting of the International Union of Crystallography in Perth, Australia. And when I showed these results, these were the results that I showed. When I showed these results, they said, okay, Danny, now you're talking. Now we can accept what you are saying. Now we are willing to form a committee, and they formed a committee to study non-periodic materials, and that committee came up with the definition that I have shown you before, that mild, very humble definition. So in 1987, acceptance was there. However, from 1987 to 1984, the resistance or the objection didn't die. And it didn't die because of one person. And that person was Professor Linus Pauling. Now, Linus Pauling was an eminent chemist, probably arguably the most eminent scientist of the 20th century, the idol and father of the American Chemical Society. And he was, I don't know if, I'm sure that some of you saw him giving speeches. He was a very flamboyant speaker. He stood on stages and he moved his hand and he said, Danny Schachtman is talking nonsense. There are no quasi-crystal, just quasi-scientists. And the crowd was, whoom. So he was not alone. He had the American Chemical Society behind him, and there were very many scientists who said the following: we don't understand anything in this. But here is Linus Pauling, and here is Danny Schachtman, and clear, right? Wrong. He was wrong from day one. What he claimed was that quasi-periodic materials are really twinned periodic crystals, which I knew at that time for many years that they are not. I knew from day one that there are no twins there. And he was standing on stages pulling, from under the table a model like this. Here, this is a structure and if you twin it this way and that way, it will give you the diffraction pattern. Wrong. And scientists around the world, immediately after he published the paper, said, wrong, Professor Pauling. This is why you're wrong. And he said, okay. Let me show you a larger model, thousands of atoms per unit cell. This will do the trick. No. Okay. He went the wrong way. Okay. In 1984, Linus Pauling, Professor Linus Pauling died, and with him, the opposition to quasi-periodic material died. So it took 10 years from the day of publication until the opposition died. Very long time in such a simple thing, something simple discovery. A simple discovery from the fact of I had the results. Here are the results. Here are the diffraction patterns. Here are the models. Here it is. Right? So people ask me, how come they do not believe it? And at the end of my talk, I will explain why it is. Several people contributed a very seminal contribution. Roger Penrose and Alan McKay. Roger Penrose showed that you can tile a plane with two rhombi and tile it without gaps, and one is a thin rhombus, another one is a thick rhombus, and it had five-fold rotation symmetry and no repeating motif. The tiling was aperiodic. So this was the great discovery. What Alan McKay did was to take Roger Penrose's drawings, shine a laser beam, and show by optical diffraction that they give five-fold rotation symmetry diffraction pattern. And he published this paper in 1981. Okay, I didn't know, I knew about Roger Penrose, of course, everybody knew, but I didn't know about Alan McKay's results, which brings other people into the game. Ilan Blech was the first person who collaborated with me and proposed the model that was published in the first paper that we sent together, but not in the second paper that was the first to appear. So this is Ilan Blech. And of course, Dov Levine and Paul Steinhardt. Dov Levine is a professor at Technion. Paul Steinhardt is a professor now in Princeton. And they proposed the mathematical model based on Penrose tiles and Alan McKay diffraction pattern. So these are really important contributors.